Today's lesson is on infinite geometric sums. First of all, let's make sure we understand what it means to be infinite. The opposite of infinite is finite, meaning it has an ending, where infinite means never ending. The first word I always think of when I hear infinite is forever. Something goes forever. And you could even think about, like in geometry, when you learn about a line segment versus a line. A line segment has a beginning and an end. So it is finite. It is measurable. Whereas a line or even a ray is immeasurable. You can't even measure it. It's boundless, whereas finite is bounded on both ends. Now, I also want you to understand the difference between something being convergent and divergent. A little different than finite and infinite. When you normally think about convergent, you think about things coming together or converging, like the cops converge on the criminal, you think of them closing in from all directions, But to diverge, you think about things spreading out. Just think if something is divergent in math, it has no sum. You could also think of a sequence that just gets bigger and everything you add just gets bigger and bigger. So how could this ever have a sum if what you're adding to it gets bigger? Whereas a convergent sequence, we're going to notice that it will converge on a sum if what you're adding continues to get smaller and smaller until it doesn't even matter anymore. And I guess the best way that I could explain converging on a sum, because you might say it will never equal an exact number if you keep adding something, and that might be true, but we say it converges on a number. For example, if you take these numbers here and we go back to how we first learned fractions, you might say 1/2 means make two equal parts, and then we take one out of the two. But let's say we add a fourth to that. These are four equal parts, so I'm going to add a fourth. And then an eighth would be half of that, and a 16th, and a 32nd, and a 64th, and a 128th. And we keep adding half of what's left. Notice we will never get out of this box. Technically, you could say we would never quite fill it up, but we're converging on a sum. And this series happens to have a sum of 1. I'm going to teach you how to do this without drawing boxes and shading. We're going to have a formula. But here's something that's critical. And I want you to realize that all arithmetic series are divergent. Okay? They have no sum. Okay? You will never be able to converge on a number like this. Will not happen. And what we usually say is you could say that the series has no sum. You could say it's divergent, or you could also say it does not exist. Does not exist. Okay, and that you'll get a lot more familiar with in calculus, the D&E terminology. Also, when we say that it converges on a sum, know that some geometric converge and some diverge. Okay, again, so some geometric series have a sum, but some have no sum. Some no sum. Okay, now let's figure out which geometric sequences will have a sum. Only the ones whose ratio, absolute value of the ratio, is less than 1. For example, if the ratio is 1/2, then you can use this formula. If the ratio is -2, well, the absolute value of -2 is 2, so that's greater than 1. So this one would have no sum, okay? So you have to look at the absolute value of the ratio. So depends on the ratio. That would have a sum. That one would have no sum. Now, so if you're asked to evaluate, the first thing you're going to do is check the ratio. Okay, so in order to check the ratio, you might want to write out the first few terms. You could do that. That'll be fine. So if I start out by plugging in 1, I get 1/4 to the 1 minus 1 is the 0 power. If I plug in 2, remember we go from 1 to infinity. Lady, how can I go to infinity? Well, if I plug in 2, I get that, and I get that. And hopefully you remember that anything to the 0 power is 1, and we get 1/4. Square the numerator and denominator, we get a 16th. And before long, you realize that if this is exponential, then the base is the ratio. The base is the ratio, okay? Not the coefficient if there is one. Well, there's the 1 is the coefficient now, but the base is the ratio, okay? So hopefully you can see we're just multiplying by 1/4. And again, remember, if it's exponential in nature, that's more geometric. If it's linear, remember that's arithmetic. Okay, so we know that we can use the formula because the ratio is 1/4 and it falls within our guidelines. So now we use this formula. Oops. I love this formula. Formula is actually the easiest one in the whole unit. So all we do is we take A1, which is 1, over 1 minus the ratio. And if you plug that into the calculator, or if you do it manually, 1 divided by 3/4 is the same as 1 times 4/3, which just gives me 4/3. And that is my answer. So if we were to keep adding these numbers to forever, it would converge on 4/3. Never, you might say it never really reaches 4/3, but we say it converges on it. So that's our sum. Example 2. Let's check this out. The ... infers an infinite sum. So the first thing we want to do is check the ratio. And remember, the way we check the ratio is to divide by the previous term. So that's 2/3. But what is 4 divided by, nope, I already did. 4 divided by 6. Now I want to do 8/3 divided by 4, which is 8/3 times 1/4 is 8/12, which reduces to 2/3. So I'm going to tell you that the ratio is indeed 2/3, which satisfies our condition of being less than 1. Okay, so now we can use our formula. S equals A1 over 1 minus R. Notice there's no N there because there's no number. It goes to forever. So A1 is 6. The ratio is 2/3. So we're looking at 6 over get a common denominator, and you're looking at 1/3 or 6 divided by 1/3 or 6 times 3, and we converge on 18. And if you look at that, 6 plus 4 is 10, and that's, a little more than 1. But if you just keep that's a little more than 2, actually. If you just keep adding these numbers up, they will converge on a sum of 18. Let's look at another example. Let's evaluate. First of all, let's see what the ratio is. 10 divided by 15 is 2/3. 5 divided by 10 is 1/2. So the first thing we see is, hey, this is not geometric. And then I notice, we have a common difference. We're going down by 5. This is arithmetic in nature. Okay? And we didn't even have to know it's arithmetic. By it not being geometric, automatically we could say has no sum. That would be one way you could answer. Or you could say the sum does not exist. Either way would be an appropriate answer. Alrighty, let's look at the next example. Notice here I wrote the terms out, but sometimes I like to give it to you in summation notation. So clearly we're dealing with infinite, and it's geometric. You could write a few terms out, but let's remember that a sub n is a1 times r to the n minus 1. So if you look at this is your a1, and this is your ratio to the n minus 1. Now, if it's not in this exact format, you might want to write out a few terms in order to understand better what's going on. But this one with the n minus 1 is a dead giveaway. Okay, that's our A1 and that's our R. So what I'm going to do now is notice that the ratio equals 3/4, which is less than 1. So I'm in excellent shape again. And S equals A1 over 1 minus R. A1 is 5/3. The ratio is 3/4. Remember that we're confident with our fractions, so I'm just getting common denominators. So that's 1/4, and we have 5/3 divided by 1/4, or 5/3. Flip that second fraction, and I get 20/3. And that is my sum. If I were to add, starting with 1 and going forever, I'd get 20/3.